Right now, as you're watching this, something invisible is passing through your body. Not air, not radiation. Something that doesn't glow, doesn't reflect, doesn't cast a shadow, and has never once been directly seen by any human being in the entire history of our species. And yet, without it, you wouldn't exist. The Earth wouldn't exist. Not a single star in the night sky would have ever formed. It makes up 85% of all the matter in the universe, and after nearly a century of searching, we still have absolutely no idea what it is. Until now, this is the story of dark matter. And honestly, it's one of the most humbling mysteries in all of science. Because here we are, in 2026, with telescopes that can peer 13 billion years into the past, particle accelerators that smash atoms at nearly the speed of light, detectors buried a mile underground in abandoned mines, and we still cannot answer one of the most basic questions about the cosmos. What is most of the universe actually made of? Let's start at the beginning. And by that, I mean 1933, in Pasadena, California, where a brilliant, foul-tempered Swiss astronomer named Fritz Zwicky was about to stumble onto something that would take the scientific world almost 4 decades to take seriously. Zwicky was studying the Coma Cluster, a massive swarm of over 1,000 galaxies, about 320 million light-years from Earth. He wanted to figure out how much the cluster weighed. Simple enough, right? You look at how fast the galaxies are moving, apply some gravitational math, and you can work backwards to estimate the total mass holding everything together. It's a technique called the virial theorem, borrowed from thermodynamics, and Zwicky was the first person to ever apply it to a galaxy cluster. So, he crunched the numbers. He looked at the velocities of 8 galaxies within the Coma Cluster, using redshift data published by Edwin Hubble and Milton Humason. And what he found made no sense. The galaxies were screaming through space at velocities exceeding 1,000 kilometers per second. Based on the visible matter he could account for, those galaxies should have been drifting along at maybe 80 kilometers per second. They were moving more than 10 times too fast. At those speeds, the cluster should have ripped itself apart billions of years ago. The gravity from the stars and gas simply wasn't strong enough to hold it together. And yet, there it was, intact, bound, stable. Something else was there, something massive, something invisible. Zwicky called it Dunkel Materie, dark matter, and he published his findings in a German language paper in Helvetica, Physica, Acta. Now here's the thing about Fritz Zwicky. The man was a genius, but he was also, by all accounts, incredibly difficult to work with. He once referred to his fellow astronomers as, and I'm quoting him directly here, spherical bastards. Because, as he explained, no matter which way you look at them, they're just bastards. So you can imagine that when this combative Swiss guy showed up claiming the universe was full of invisible matter that nobody could see, the scientific community basically shrugged and moved on. His discovery was ignored for nearly 40 years. But Zwicky wasn't wrong. He was just ahead of his time. Fast forward to the late 1960s. A young astronomer named Vera Rubin is working at the Carnegie Institution of Washington with her colleague Kent Ford, who has just built a revolutionary new spectrograph, a device that could measure the light from distant galaxies with 10 times the sensitivity of anything that came before. And Rubin decides to point it at our nearest galactic neighbor, the Andromeda galaxy. What she wanted to do was simple: measure how fast stars orbit at different distances from the galaxy's center. According to everything physicists knew about gravity, stars near the center should orbit fast, and stars farther out should orbit slower, just like how Mercury zips around the Sun much faster than Neptune does. You'd expect the rotation curve, that's the graph plotting speed versus distance, to rise steeply near the center and then gradually fall off. That's not what she found. The rotation curve was flat. Stars at the very edge of Andromeda, 78,000 light-years from the core, were moving at roughly 270 kilometers per second, just as fast as the stars near the center. The curve didn't drop. It just kept going, flat as a ruler, all the way out. Rubin later recalled, and this is one of my favorite quotes in all of astronomy, "By the end of the first night, we were puzzled by the shape of the rotation curve." Puzzled is an understatement. What she was seeing meant that galaxies contain enormous amounts of mass that we simply cannot see. Mass that extends far beyond the visible disk of stars. If that mass weren't there, those outer stars would be flung into intergalactic space like water off a spinning wheel. But Rubin was careful. She knew one galaxy wasn't enough. So over the next decade, she and Ford observed galaxy after galaxy after galaxy. By 1980, they had mapped rotation curves for 21 spiral galaxies. Every single one was flat. Then 40, then 60, all flat. As she put it, all you had to do was show them a picture of the spectrum. It just piled up too fast. The evidence was overwhelming. Every spiral galaxy they looked at was behaving as though it was embedded in a massive, invisible halo of something. Something that outweighed the visible stars and gas by a factor of 5 to 10. Dark matter wasn't a quirk of one cluster. It was everywhere. And here's something that always gets me about Vera Rubin. When she first tried to observe at Palomar Observatory, she was told women weren't allowed. There was no women's restroom, so she reportedly cut out a paper figure of a woman and taped it to the men's room door. She wasn't going to let anything stop her. She went on to study over 75 spiral galaxies and fundamentally changed our understanding of the cosmos. She received the National Medal of Science in 1993 and the Gold Medal of the Royal Astronomical Society. But she never received the Nobel Prize, an omission that many in the physics community still consider one of the most glaring oversights in the award's history. She passed away on Christmas Day 2016 at the age of 88. Today, the Vera C. Rubin Observatory in Chile carries her name, and it's already returning its first images as part of a 10-year survey of the southern sky. At a meeting of the International Astronomical Union in 1985, Rubin said something that I think perfectly captures the dark matter mystery. In a spiral galaxy, the ratio of dark to light matter is about a factor of 10. That's probably a good number for the ratio of our ignorance to knowledge. So we know dark matter is out there. We can see its fingerprints everywhere. But can we prove it's real stuff, and not just a sign that our theory of gravity is wrong? Enter the Bullet Cluster. In 2006, astronomers studying two galaxy clusters that had slammed into each other at about 10 million miles per hour found something extraordinary. The collision, one of the most energetic events since the Big Bang, happened about 150 million years ago, 3.7 billion light-years away in the constellation Carina. And when they looked at the aftermath using NASA's Chandra X-ray Observatory, the Hubble Space Telescope, and gravitational lensing analysis, they saw the three components of the clusters had separated. The stars, the actual galaxies, had passed through each other mostly unaffected. Stars are tiny compared to the space between them, so they just sailed past one another. The hot gas, which makes up most of the normal visible matter in a galaxy cluster, slammed together and slowed down dramatically. You can see it in X-ray images as two bright pink clumps. But the dark matter, mapped by how it bends light from background galaxies, kept right on going. It didn't slow down. It didn't interact with the gas. It just ghosted straight through, like it wasn't even there. And that separation, that gap between where the normal matter ended up and where the mass actually is, that's the smoking gun. Because if dark matter were just an illusion caused by modified gravity, the mass should follow the gas. It doesn't. The mass follows the dark matter. It's real. It's there. It's something. But what? That's the trillion-dollar question, and honestly, it might be the most important unsolved problem in physics. The leading candidate for decades has been something called a WIMP, a weakly interacting massive particle. These would be particles roughly 1 to 1,000 times the mass of a proton that interact with normal matter only through gravity and the weak nuclear force. They'd be everywhere, streaming through you right now, billions of them every second, but so weakly interacting that they'd pass through the entire Earth without touching a single atom. To hunt for WIMPs, scientists have built some of the most extreme experiments on the planet. The LUX Zeppelin detector, or LZ, sits nearly a mile underground at the Sanford Underground Research Facility in South Dakota. It's a 10-ton chamber of ultra-pure liquid xenon, so pure and so shielded from cosmic rays that it can detect the faintest flash of light from a single atomic collision. 250 scientists from 37 institutions are watching it around the clock. In December 2025, they published results from 417 live days of data collection, probing for WIMPs with masses between 3 and 9 times the mass of a proton, the tightest constraints ever measured. And they found nothing. No WIMPs. But here's the beautiful part. They did detect something. Solar neutrinos. Actual neutrinos from the core of the Sun, hitting their xenon atoms, which tells you just how insanely sensitive this detector is. It can catch neutrinos from 93 million miles away, but still can't find dark matter. Then there's Super C DMS, buried 6,800 feet underground in a Canadian nickel mine at Snowlab near Sudbury, Ontario. This experiment has just cooled its detectors to thousandths of a degree above absolute zero, roughly 1,000 times colder than outer space. At that temperature, the atoms in its germanium and silicon crystals are almost perfectly still, making the detectors sensitive enough to feel the faintest nudge from a dark matter particle. 24 detectors, 30 kilograms total, waiting in the cold and the dark. Science-quality data collection is scheduled to begin mid-2026. But maybe dark matter isn't a WIMP at all. Maybe it's something even stranger. There's the axion, a particle first proposed in 1978 by physicists Frank Wilczek and Steven Weinberg. Axions would be absurdly light, millions or even billions of times lighter than an electron. But there'd be so many of them that they could account for all the dark matter in the universe. The way you hunt for axions is beautifully weird. You build a microwave cavity, stick it inside an enormously powerful magnet, cool it to near absolute zero, and weight. If an axion drifts through the magnetic field, theory says it should convert into a photon, a tiny flash of microwave light, like tuning into a cosmic radio station you've never heard before. The ADMX experiment at the University of Washington has been slowly turning that dial for years, scanning frequency ranges one tiny slice at a time. And in April 2025, something genuinely exciting happened. Scientists at Harvard, Northeastern, and a dozen other institutions across 5 countries actually observed axion quasiparticles in a lab for the first time. They used a material called manganese bismuth telluride, and with ultrafast optics, they caught these quasiparticles in action. Now, these aren't actual dark matter axions floating in from space. They're quantum analogues, laboratory recreations of the behavior the theory predicts. But it's the first time anyone has seen that behavior with their own instruments. It's like finding a footprint before you find the animal. And then there are ideas that get even wilder. Fuzzy dark matter, where the particles are so incredibly light that their quantum wave nature stretches out over entire galaxies, creating interference patterns in the cosmic web. Self-interacting dark matter, where dark matter particles can actually collide with each other, but not with us, potentially triggering gravitational collapses that seed supermassive black holes. And as of April 2026, a team at Fermilab and CISA published a paper proposing that dark matter might not be one particle at all, but two different species that must interact with each other to produce a detectable signal. That would explain why we see a mysterious gamma-ray glow at the center of our Milky Way, but not in smaller dwarf galaxies where the particle ratio might be different. Speaking of that gamma-ray glow, let me tell you about what might be the most exciting development in this entire story. In November 2025, Professor Tomonori Totani at the University of Tokyo published an analysis of data from NASA's Fermi Gamma Ray Space Telescope. He detected a halo of gamma rays with photon energies of 20 billion electron volts extending outward from the Milky Way's galactic center. The energy levels, the intensity pattern, the shape of the glow, they all match almost perfectly what decades of theoretical models have predicted should happen when two dark matter particles collide and annihilate each other. The implied particle mass is about 500 times that of a proton, right in the sweet spot for WIMPs. After nearly 100 years of searching, this could be the first direct observational evidence of dark matter. But we have to be careful. There's another explanation. A population of old, rapidly spinning neutron stars called millisecond pulsars could also produce a similar glow. The data can't yet tell us which it is. Future observations, especially from the Cherenkov telescope array coming online around 2027, may finally settle the question. And then, in January 2026, JWST dropped a bombshell. Using 255 hours of observation on a patch of sky, about 2.5 times the size of the full moon, the James Webb Space Telescope mapped nearly 800,000 galaxies and produced the most detailed dark matter map in human history. It's twice as sharp as anything ever made before. Where Hubble could resolve about 71 galaxies per square arc minute, JWST sees 129. And what this map revealed is nothing short of breathtaking. Dark matter isn't scattered randomly. It's organized into a vast cosmic web with dense nodes connected by long filamentary bridges stretching millions of light years. and enormous voids of near emptiness in between. And wherever you find a strand of dark matter, you find galaxies strung along it like beads on a thread. Wherever there's a massive clump, there's a galaxy cluster. The two grew up together, as one member of the research team put it. And here's the part that genuinely gave me chills. According to NASA's analysis, dark matter didn't just shape where galaxies formed. It shaped when they formed. By clumping together early and pulling in ordinary matter through gravity, dark matter accelerated star formation. Those first generations of stars forged hydrogen and helium into heavier elements, carbon, oxygen, iron, the elements that eventually formed rocky planets. Planets like Earth. In a very real sense, dark matter helped create the conditions for life. You exist, in part, because of something you will never see. Meanwhile, other JWST observations are shaking the foundations of what we thought we knew about dark matter's fundamental nature. Astronomers studying extremely ancient galaxies at redshifts of 3 to 8, meaning we're seeing them as they looked in the first 500 million years after the Big Bang, found something the standard model didn't predict. These galaxies are elongated, stretched out, prolate, and when you run simulations using cold dark matter, the kind that moves slowly and clumps into small dense nuggets, you get spheroidal galaxies, round blobs. That doesn't match. But when you run simulations using warm dark matter or wave dark matter, where the particles are lighter and move faster, creating smoother, more filamentary structures, you get elongated galaxies. Just like what JWST sees. A paper published in Nature Astronomy in 2026 by Alvaro Pozo and colleagues concludes that the shapes of early galaxies are sensitive to the smoothness of the underlying dark matter filament network, which means the first galaxies JWST is revealing could be telling us what dark matter actually is. And if all of that wasn't enough, researchers at the University of Minnesota and Paris-Saclay published a study in January 2026 proposing that dark matter may have been born hot, not cold, moving near the speed of light just after the Big Bang, then gradually cooling over time to become the calm, structure-building force we see today. If that's true, it overturns a fundamental assumption that cosmologists have relied on for decades. In February 2026, astronomers with the Royal Astronomical Society floated perhaps the most radical idea of all. What if the supermassive black hole at the center of our galaxy, the famous Sagittarius A star, isn't a black hole at all? What if it's actually an enormous, ultra-dense clump of dark matter? A dark matter structure with a compact core that mimics a black hole's gravitational pull, surrounded by a broad halo that shapes the galaxy's outer rotation. It would explain the same observations without requiring a singularity. That's still a minority view, and most astrophysicists remain skeptical. But the fact that the idea can even be proposed and taken seriously tells you how rapidly our understanding is evolving. So where does that leave us? We know dark matter is real. We know it makes up about 85% of all the matter in the universe. We know it shaped the cosmic web, triggered the birth of galaxies, and indirectly made your existence possible. We know it doesn't emit light, doesn't absorb light, doesn't reflect light, and passes through ordinary matter like it isn't there. We can map it, weigh it, and trace its influence across 13 billion years of cosmic history. But after 93 years of searching, Since Zwicky first scribbled Dunkel Materie in his notebook in 1933, we still don't know what it is. And I think that's actually beautiful, because it means the universe is still keeping secrets. It means there are discoveries ahead of us that will be every bit as revolutionary as Zwicky's insight or Rubin's flat rotation curves. Right now, detectors are sitting in the cold darkness under a mile of rock, waiting for a single particle to make itself known. Telescopes are staring at ancient light, looking for the faintest clue. And somewhere, maybe in a lab that hasn't been built yet, a scientist who might not even have been born yet will finally crack this open. Vera Rubin said it best. Still more mysteries of the universe remain hidden. Their discovery awaits the adventurous scientists of the future. I like it this way. So do I. If this video blew your mind, do me a favor and hit that subscribe button so you don't miss what comes next. Drop a comment and tell me, what do you think dark matter is? A WIMP? An axion? Two particles that need each other? Or something nobody has even imagined yet? And if you know someone who would love this, share it with them. Because the universe is too incredible to keep to yourself. I'll see you in the next one.